So in this video we are continuing to work on 6C, the Stoichiometry Practice packet. And we are starting with number 17. So this equation up here is intended to be used for 17 through 21. So we need to start by balancing this equation, and then we can use it to answer all of the subsequent questions. So we have 2 nitrogens on our reactant side, so we need to put 2 in front of NH3 on the product side. And now we have 6 hydrogens on the product side, so we need to put a 3 on the reactant side. And then let's just fill in a 1 for nitrogen. So number 17 says how many moles of hydrogen are necessary to produce 3.45 moles of ammonia in the presence of an excess of nitrogen. So excess just means that we have lots of extra nitrogens. We don't need to worry about how much of it we have. So let's write our given value, 3.45 moles of ammonia, so NH3. And we're doing a mole-to-mole conversion, which we said, looking at our chart, mole-to-mole conversions are just one single step. So we need one conversion factor, and then we will have our answer. So on our conversion factor, we need moles of NH3 to cancel. And we want to get to moles of hydrogen. So moles of H2 will go on top. And then we just need to look at our balanced chemical equation. There are 2 moles of NH3 and 3 moles of H2. So it's a 3-to-2 ratio. So then let's just type this into our calculator, 3.45 times 3, and then divided by 2, which gives us 5.175. But in our problem, we only have 3 significant figures in our value, so we need to round this to 5.17. So this 5 is going to make the 7 round up to an 8, so 5.18. And then we need our units. So moles of NH3 cancels, so we're left with moles of H2, so our units are moles of H2, which matches what the problem says. So there's our final answer here. In our next problem, it says how many grams of hydrogen are necessary to react completely with 50 grams of nitrogen. So we're doing a gram-to-gram conversion here. So we know that that's going to require 1, 2, 3 steps. Gram-to-gram conversion is going to require 3 steps. So let's see, we're starting with 50, 50.0, so this has 3 significant figures, grams of nitrogen into, and we're going to need 1, 2, 3 steps to get us our answer. Our first step is going to take grams of N2 into moles of N2. Our second step needs to take moles of N2 into moles of our new substance, which is hydrogen. And then our third step needs to take moles of hydrogen into grams of hydrogen, because that is what the problem is asking for. So, to figure out our mole-to-mole ratio, we just need to look at our balanced equation. So there is 1 mole of N2, and there are 3 moles of H2, so it's a 3-to-1 ratio. I'm going to fix that 1 there. And to figure out how many grams are in a mole, we need to look at the periodic table, and for the mass of nitrogen, which I'm looking at, the mass of 1 nitrogen is 14.007, but we need to multiply that by 2. And remember we said 14.00 something, we can round that to 14. So I'm going to say this is approximately 28 grams per mole. So for nitrogen, N2, our molar mass is going to be 28 grams per 1 mole. Then for hydrogen, H2, hydrogen's mass is 1.008, so we can round that to 1. And then we have 2 hydrogens. 1 times 2 is 2 grams per mole for hydrogen. So 2 grams of hydrogen per 1 mole. So now we just need to multiply and divide. We can cancel some units first if we want to. So grams of nitrogen, moles of hydrogen, and we're left with grams of H2. And then I'm also going to cancel this 2. 2 and 28 are both divisible by 2, so this 2 is going to divide by 2 become a 1. This 28, when you divide that by 2, you get 14. So I'm just simplifying this a little before I put it in my calculator. You can also just type all the numbers into your calculator. Now I have 50 times 1 times 3 times 1. So I just need to do 50 times 3, which gives me 150. And now I need to divide by what's left in the denominator. 1 times 14. So just 14 divided by 14. So I got 10 point, a bunch of decimals, 10.71428. But looking at my problem, I can only have 3 significant figures, so I need to round 1 to 7. This 1 makes the 7 round down to 7, so my final answer is 10.7, and my units are grams of H2. Alright, continuing on. I'm going to actually keep the equation up here so we have it as a reference for doing the next problem, since it's the same equation. So this next problem says how many liters of hydrogen are necessary to form 6.5 moles of ammonia. So that's my given value, unit, and substance, and I want to know how many liters of hydrogen are necessary. So I already have my balanced equation, so I'm going to start with 6.5 moles of ammonia, which is NH3. And then if I'm going from moles of one thing to liters of something different, I'm going to need moles to liters. So that's 2 steps. So I need 2 conversion factors. My first conversion factor is going to take me from moles of NH3. Because we're already in moles, we're going to go from moles of one thing to moles of our new thing. Moles of hydrogen. And my second conversion factor is going to take moles of hydrogen into liters of hydrogen. So to figure out my mole to mole ratio, I look at my chemical equation. So there's 3 H2s and 2 NH3s. And then I know that for every ideal gas, I know that 1 mole is equal to 22.4 liters. So I put that 22.4 next to the liters of H2 and then 1 mole of H2. So now we can cancel things, moles of NH3, moles of H2, and we're left with liters of H2, which is what we wanted. So that's good. So then we need to put it in our calculator. 6.5 times 3 times 22.4. And then we're going to divide that by 2. A common mistake is that people forget to divide by the number in the denominator, so don't forget about that. So I got 218.4, but my problem only has 2 significant figures, so I'm going to need to round this to just 2 significant figures. So this 8 makes 1 round up to 2, so I have 2, 2, and then because I need a placeholder here, I'm going to put a 0. 220 has 2 significant figures. I don't want to put a decimal point because if I put a decimal point, that makes this value now have 3 significant figures. So 220, my units are liters of H2. It's also correct to put this in scientific notation, so you could put 2.2 times 10 to the second power liters of H2. Either way is a correct way to write your answer. So I'll box in those values here. Our next problem says how many grams of ammonia are produced in the reaction of 78 grams of nitrogen. So we already have our balanced equation, so we're going to start with our given value, 78.0 grams of N2. And then to go from grams of one thing to grams of another thing, that's going to require 1, 2, 3 steps. So 3 conversion factors, so times 1, times 2, times 3 conversion factors. And that will get us our answer. So our first conversion factor needs to take grams of N2 into moles of N2. And then our second conversion factor will be our mole to mole conversion, so moles of N2 into moles of our new thing, so moles of ammonia, NH3. And then our third conversion factor will take moles of NH3 into grams of NH3. So to figure out our conversion factors, our values, for our mole to mole ratio, we look at our equation, so 2 moles of NH3 for every 1 mole of N2. And then for our gram to mole conversions, we know that 1 mole of N2, we already calculated that one, I think, before, but we'll just do it again. Nitrogen by itself is 14, so 14 times 2 is 28. So there are 28 grams of N2 per 1 mole of N2. And then NH3, I don't think we've calculated that one yet, so NH3, we have 1 nitrogen, so 14 plus 3 times 1, because the molar mass of a hydrogen atom is 1 approximately. 14 plus 3 gives us 17 grams per mole. This should also be labeled grams per mole. So 17 grams of NH3 per 1 mole of NH3. Perfect. So now we just need to cancel our units and multiply and divide. So grams of N2 cancels, moles of N2 cancels, moles of NH3 cancels out. So now I can reduce this a little bit further if I want to. So 2 and 28 can reduce to 14 and 1. And that's all I see that I could reduce here, but I'm not going to. So now we do 78 times 1 times 1 times 17. 78 times 17 divided by just 14 on the bottom. And that gave me 94.71428, but I need to round to 3 significant figures. 1, 2, 3. Now this 1 makes the 7 round down. So this will be 94.7 grams of NH3. Alright, and then number 21, the last problem that goes with this chemical equation. It says how many ammonia molecules, so that's what we're looking for, ammonia molecules, are produced when 12.1 grams of hydrogen react with excess nitrogen. So with extra nitrogen, if 12.1 grams of hydrogen react, how much ammonia will be produced? So this is a gram to molecule conversion, so grams of one thing to particles or molecules of another. That's 1, 2, 3 steps. So let's write. I'm going to have to move this up and cover our equation for a second here. So let's write our given value, 12.1 grams of H2. And we're going to need 1, 2, 3 conversion factors. Our first conversion factor has grams of H2 on bottom, and we're going to go to moles of H2. Our second conversion factor is going to take moles of H2 and convert to moles of our new substance, so moles of ammonia, NH3. And then our third conversion factor is going to take moles of NH3 and convert it to molecules of NH3. Molecules of NH3. So now we just need some numbers. So we know that 1 mole of H2 is equal to 2 grams of H2 because each hydrogen atom has a mass of 1. So I'll write that down here. 1 times 1 equals 1 gram per mole for H2. Or, sorry, 1 times 2 equals 2 grams per mole. This is why we write it out, so we don't make these mistakes. 2 grams in 1 mole. Then our mole-to-mole ratio, so moles of H2 for moles of NH3, so 2 NH3s and 3 H2s. 2 NH3s and 3 H2s. And then we have molecules in moles. So we know that 1 mole of anything is equal to Avogadro's number of molecules, 6.02 times 10 to the 23rd molecules. So now let's cancel some things out. Grams of H2 cancels out, moles of H2, moles of NH3, and we're left with molecules of NH3, which ammonia molecules is what we were looking for. Then we can also cancel out these 2's because they're one on top and one on bottom. And I think that's it. We'll put the rest in our calculator. 12.1 times 1 times 6.02 e to the 23rd, and then divided by 3. So that gave us 2.428 times 10 to the 24th. It's a big number, but that makes sense because we were looking for a number of molecules. So now we just need to correct our significant figures. We have 3 significant figures in our given value. So when we write our answer, we can can put 1, 2, 3. This 8 makes the 2 round up, so this is our final answer will be 2.43 times 10 to the 24th. And our units are molecules of NH3. Box that in. There's our other paper of all our work we've done. So this next one says use the reaction below to answer questions 22 through 24. So we can go ahead and balance this equation, and then we can use it for several questions in sequence. So first I would just want to point out that this is a combustion reaction, and we have oxygen in 3 different places. So we always want to leave oxygen to balance last, because it's going to be potentially more difficult to balance oxygen than to balance the other things in our equation. So we'll work with the easy things first. So we'll first look and see carbon. So there's 3 carbons, and there's only 1 over here, so we're going to put a 3 in front to balance the carbon. And then let's look at hydrogen. We have 8 hydrogens on the reactant side and only 2 on the product side, so I'm going to put a 4 in front of the hydrogen. So 2 times 4 gives me 8. And now we're going to look at oxygen. So we have 2 times 3, so 6 oxygens from CO2. And then we have 4 oxygens, 4 times 1, from H2O. So that gives me a total of 10. So that worked out nicely, because now I know I can put 5 times 2 to give me 10 oxygens. And I'll just fill in my 1 in front of C3H8. So that's why we always leave oxygen until last, or anything that's in more than 2 places in our chemical equation. Oxygen's in 3 different places, so we want to leave that till last to make it as easy as possible for ourselves. Now that we have a balanced equation, let's look at our first problem. It says how many moles of oxygen are necessary to react completely with 4 moles of propane, and it tells us that propane is C3H8. So that is not a substance name that you would be expected to know just yet. So we're going to start with 4 moles of propane, which is C3H8. And then we're going from moles of one thing to moles of another. And we know a mole to mole conversion is just 1 step. So moles of C3H8 goes on bottom, and then we're converting to moles of oxygen. So moles of O2 goes on top. And now we just need to look in our chemical equation. So we have 1 mole of C3H8, and then we have 5 moles of O2. So we can do this one in our head, cancel our units out. We'll be left with moles of O2. 4 times 5 gives us 20 moles of O2. And our value is just 4, so 1 significant figure is fine. 20 already just has 1 significant figure. Our next problem says if 20 liters of oxygen are consumed in the reaction, so 20 liters of oxygen is our given value, unit and substance, 20 liters are consumed, how many liters of carbon dioxide are produced? So we're looking for liters of carbon dioxide. So the problem's flipped around here. The given value is at the beginning, but it still has a value, a unit, and a substance, so we can know that that's our given value. And then it says how many liters of carbon dioxide, so we know that's what we're looking for. So we're doing a liters of one thing to liters of another thing conversion, so we know that's going to be 3 steps. So 20 liters of O2. And then we're going to have 1, 2, 3 steps to get us to our final answer. First step is going to take liters of O2 to moles of O2. Our second step is going to take moles of O2 to moles of our new thing, which is carbon dioxide, CO2. And our third step is going to take moles of CO2 to liters of CO2. So we know that 1 mole of any gas fills 22.4 liters. So I fill that in there. And the same thing over here, 1 mole of a gas fills 22.4 liters. And then we just need our mole to mole ratio. So there's 3 CO2s and there's 5 O2s. So now we can cancel some things out. Liters of O2 cancels, moles of O2 cancels, and moles of CO2 cancels. We can also cancel out these 22.4s because there's one on top and one on bottom, so we'll cancel those out as well. And now we can just plug the rest into our calculator, or do it in our head. 20 times 3 is 60 over 5, so 60 divided by 5 is going to give us 12, and our units are liters of CO2. And actually, this is not correct significant figures because it gave us 20 liters of oxygen. That only has one significant figure, so we need to round this. So 12, one significant figure, 12 would round down to 1. So our final answer should be 1, fill in the place with 0 liters of CO2. So that's our correct rounded answer. 10 liters of CO2. And with that, we can proceed to number 24, the last problem in relation to this equation. It says when 82 grams of propane react with excess oxygen, so a whole bunch of extra oxygen, how many grams of water are produced? So how many grams of water, grams of H2O, are produced? So we have a gram to gram conversion. So we know that's going to be 3 steps. So we're going to start with 82 grams of propane, which is C3H8. And we're going to have 1, 2, 3 steps here. So, since we have grams, we do need to find the molar mass of these substances. So C3H8 is going to be 3 times the mass of carbon, which is 12.011, plus 8 times 1. So when we do that, that's going to give us a molar mass 3 times 12.011 plus 8 gives us 44.033. And then we're also going to need the mass of water. So H2O, we're going to have 2 times 1 mass of hydrogen plus the mass of oxygen, which is approximately 16, which gives us 18 grams per mole. 44.033 grams per mole. So now we have our molar masses, so when we need those, we can fill them in. So, to make our stoichiometry work, we need grams of C3H8 to cancel. So that goes on the bottom. And we're first going to convert to moles of C3H8. Our second conversion factor will take moles of C3H8 and convert to moles of our new thing, moles of water, H2O. And then our third conversion factor takes moles of H2O and converts it into grams of H2O. We already know how many grams are in 1 mole because we just added it up. There are 44.033 grams per mole for C3H8. And then in 1 mole of water, there are 18 grams for H2O. So we just need our mole ratio. So we have 4 moles of H2O and 1 mole of C3H8. So now we can go through and cancel our units. Grams of C3H8, moles of C3H8, moles of H2O, and we're left with grams of H2O. I don't see anything that we can cancel, so we're just going to type all this into our calculator. So we have 82 times 1 times 4 times 18 on top. And then we're going to divide by 44.033. 44.033. And that gave us 134.08125, but we need to round this to just 2 significant figures. So 1, 2, this 4 makes it round down to 3, so we round to 1, 3, and then we need to fill in a 0, 130, and grams of H2O.